Is it true that for any sets a, b, and c, a times b minus c is equal to a times b minus a times c? Give either a proof or a counterexample to justify your answer. Well, I think it's true because it looks like you're just distributing the a, right? Well, okay, that's not so convincing. So let's at least try and draw a picture to convince ourselves that it might be true. We could have a set A right here, and maybe a set B right here, and so A times B would be this rectangle. All right, and then we're supposed to take A times C away from that, so I should also have a set C, which can be maybe from here down to somewhere in here. Okay, and so A times C is this rectangle, something like that. And okay, when we take a times b and then we subtract away a times c, what we're really losing is this part here, right? So this bottom rectangle is what's left, and it looks like that is exactly a times this set here, which is b minus c. Okay, so this bottom rectangle here is what we get on the left side and the right side. So it looks true. Let's try to prove it. And I'm going to do this one by, well, okay, first of all, we have our given and our goal, and to prove the equality of sets, we want to say for all p, p is on the left side if and only if p is on the right side. Okay, so let p be arbitrary. All right, I'm not going to write that here just because we're being a little bit sloppy, but our reader will understand what we're up to. In fact, I'm not even going to use p. I'm just going to go ahead and write an ordered pair x, y, because we know if something's an element of a Cartesian product, it's going to be an ordered pair. Okay, so there I'm going to miss out on some quantifiers that way, which will make my proof a little bit simpler and easier to read. So those are some stylistic decisions that I'm making. All right, so what I'm going to show in my proof is that if I have x, y in the left side, that's equivalent to having x, y in the right side. All right, so that's what I'm saying in my opening line of my proof here. And I'm just going to do a chain of equivalences. Okay, so x, y. I tried starting with x, y on the left side, and it was a little bit unclear about how to get to the right side, so I ended up trying it in the other direction, and it was a little clearer. So let's do that. All right, so first thing I'm doing is using the definition of set difference, right? For x, y to be in this difference means that it's in the first part and it's not in the second part. And from there, well, in the first part here, I'm using the definition of Cartesian product. That means that x has to be in A and y has to be in B. And then here, x not being in A times C, well, that means it's not true that x is in A and y is in C. Okay. In the next step, I'm going to use what's that called? De Morgan's law to distribute the negation. So I get x not in A or y not in C. And you know, my eventual goal, if you look at the definition of where we're headed, is to get down to a single A. And so my idea was maybe I should switch the order of these two statements, bring the x in A closer to the x not in A, and then just rewrite my parentheses. Well, and make one of them disappear, I guess. I should probably add that back in there. And now I can take this x in A and distribute it to these two terms. Okay, and so I get x in A and x not in A, or x in A and y not in C. And the nice thing here is that this is a contradiction, right? There's no way x can be both in A and not in A. So I have a contradiction or some other statement. And the only way that can be true is if this other statement is true. So we can basically just drop the contradiction in the or sign. And this statement here comes over here. And now that's pretty close to where we want to end up. Okay, just drop the parentheses or brackets here, and whoops, go ahead and move the x in A back in front. Okay, alphabetical order. And so the y in B is here. I have y in B and y is not in C. Together those mean that y is in B minus C. And if I have x in A and y in B minus C, then the ordered pair is in A times B minus C. okay, which was the other statement that I wanted. So that finishes the proof. And you can certainly do this by making a givens and goals table, but when possible, I find this sort of chain of equivalences proof to be a little easier to come up with and a little easier to follow. Okay. The one downside is that sometimes it just gets so complicated that you can't really finish it. All right, and in that case, the proof techniques from the last chapter can sometimes make it a little more manageable. All right.